All right, welcome back, everybody. Moving on to section 1.3, I'm calling this solution methods for ODEs. We're going to see just a huge amount of ODEs, solution methods. Obviously, we can't solve every single ODE that anyone ever gives us. Some of them are just unsolvable. But we're going to cover some of the more common solution methods, especially some of the more powerful ones and the ones that you may end up wanting to use in the real world if you're ever asked to solve ODEs. And I do want to comment before we get started too much that this will probably look different from how you studied in your ODEs course. Okay, so I present a lot of theorems which, taken together, are extremely powerful. And my word that I like to use for the way I present these theorems is arcane. To a certain extent, I'm giving you all arcane knowledge, with my definition meaning powerful when used correctly, dangerous otherwise. Because the notation that I use is so strong, the way I present these theorems is so strong that you really have to be very careful about applying them correctly. If there's any part in the theorem that doesn't make sense, there's a good chance that you'll end up using it incorrectly and getting a very wrong result. So to a certain extent, I'm going to be going through all these theorems in this section. And if you're going to end up studying ODEs, this is going to be a fantastic resource for the rest of your life, this section. But if you're in this course to just kind of get a taste of PDEs, get a feel for what they're trying to do, you may not want to pay too much attention to this particular section and instead think about the next video a lot more. And because we're just going to cover examples of much more common ODEs, which is much more common maybe in the course that you took if you didn't take my previous course on ODEs. So a lot of undergraduate ODEs courses avoid all of this arcane knowledge, even though it's very powerful because it's so easy for undergraduates to misinterpret, or in some cases just can't understand at all. And so they really try to kind of lower the bar on both the power but also the level of understanding that you need to do something correctly. And it's up to you to decide how much time you want to devote to learning everything in this section, or if you'd rather just pass on to the next section where I give you a table of ODEs and their solutions, and we're going to go through some examples in the next video as well. So it's totally up to you, but I'm going to go through this section and present everything the way that I like to see it, the way that I think is the most powerful, and just be careful when you're actually working with it. We don't want anybody getting hurt. Okay, so why are we covering this? Well, it turns out that when we solve PDEs, almost always the way we're going to solve PDEs is by constructing a specific selection of curves through the domain of the PDE upon which the PDE reduces to an ODE. So since this is a curve, it only has one independent variable, right? It's got that t there. It's been parameterized by time. So there's one independent variable. And that independent variable, if I take a derivative in that independent variable, I end up with an ODE. So we're going to try to reduce a PDE into a collection of infinitely many ODEs. These are going to be called characteristic curves. And we'll try to solve a PDE by solving infinitely many ODEs that way. Or in some situations, we'll transform the PDEs. This is kind of the area of the Fourier transform and some other transforms that you may have heard of. And this will transform a PDE into a system of infinitely many ODEs. Okay, so one way or the other, the ways that we really know how to solve PDEs are by solving infinitely many ODEs. And it's the interplay of solving these infinitely many ODEs and then realizing them as a solution to the PDE that we're really going to study. What that means is that everybody in this class is going to need to know how to solve ODEs pretty well, or else, there's no hope on PDEs. So we're going to have to get good at solving ODEs. Like I said before, though, whether or not you want to solve them as well as this section tries to help you solve them is up to you. The ODEs we'll encounter in the course are going to be easier than this section's ODEs. So it's totally up to you. Let's look at this first theorem. This is the theorem that's called converting a system of d nth order ODEs. Okay, so I'm saying I have a system of d. So there are d ODEs, and they're all in nth order. We're going to convert that system into a system of nd. So there are nd ODEs, but they're all in first order. So in some sense, I'm making this copy of, we're doing d copies of nth order ODEs, and we're going to transform them to nd copies of first order. And of course, the multiplication works out just fine. Why is this useful? Well, if everything becomes a first order ODE, then all we ever need to study is a first order ODE. I mean, it's systems of first order ODEs, right? We've got ND of copies of these things. but we only need to solve the first order ODEs. And so that's a pretty useful technique to keep in mind because it lets us translate everything to first order. And the way this theorem works is we're going to say, okay, we've written this as a vector valued ODE, and that means that's why I've got my boldface x's here. So you can imagine every single one of these x's is actually in some d-dimensional space. So all of those boldface x's are in d-dimensional space. And I'm looking at the nth derivative of them, so that's why I have the nth order, and I have d copies of it because they're in d-dimensional space. And what I say is that I can take this giant system, f involves all of the derivatives of these vectors together, and you get 0 out of it. But I can translate this entire system into a new system with a new function g, but g is special in the fact that rather than considering the top derivative as being the nth derivative, the top derivative in g is just the first derivative. Okay, so really what I'm going to say is, how do we construct a g such that the solution to this equation can be delivers the solution to the earlier equation? So that's what I should say. So solving bottom delivers solution to top. That's what we want to think. So solving this bottom one, we're going to try to find the bottom one so that if we solve it, we can deliver a solution to the top. If I scroll down, what is the solution to the top? The solution to the top it will be the first d entries in the solution to the bottom. So that's how we're going to set this up. We're going to try to set it up so that we can solve a first order ODE. And if we look at the first d entries in the vector of the first order ODE, we actually recover the solution to the nth order ODE. How do we do this? So the proof actually is how we do this. So not only is this a proof of a theorem, but it actually gives us a way of constructing these objects in the theorem. So we are going to study the proof here. And we're going to consider the original ODE that we want to solve. What we're going to do once we consider that is we're going to give a new vector y a definition. So this new vector y is going to be defined by, there's my definitional equal sign, it's going to be defined by the vector x, and then I'm going to add to that vector the vector x prime. I'm going to add to that vector an x double prime and so on until I get to right below the top order, right? So my top order here is the nth order, and I'm going to add all these, or I'm going to join all of the vectors together up to 1 before the final order. So the final order was n, but 1 before the final order is n minus 1. I'm going to call this entire vector y. So this is a very large object, which is why it's in n times d dimensions. So that entire vector is going to be called y, and then that gives me that the first derivative on y will just translate to one more derivative on all of the terms in the vector. Most importantly, this very final derivative term in my original ODE will be the last entry of y prime. Okay, so the very last entry in my original ODE will be the very last entry of y prime. This is going to be useful because when I look at the function in the original ODE, this capital F, you can see y prime show up and you can see y show up, which means that in some sense this is going to be our related to g. So related to g, the vector g, which was a function of t, the vector y, and the vector y prime, because there's the vector y and there's the vector y prime. And so I've kept the vector y there, and I've actually only included the last d entries of y prime. So the last d entries of the vector y prime have been included, and the entire vector y has been included. Okay, so since f was d entries long, right, this is a system of d-dimensional ODEs, so that means f evolves in d dimensions. That means that this version of f that I've translated in terms of y also only evolves in d dimensions. And I have nd total unknowns. Okay, so if I have nd unknowns and f accounts for d of them, I can factor d out to the right, and I find out that I actually have n minus 1d unknowns unaccounted for. And when I have those nd unknowns unaccounted for, that means, or n minus 1d unaccounted for, I need to find that many more differential equations which relate y and y prime together. So I'm going to look for those. It's actually pretty easy to find them. We can find them by the following. I note that y prime, which had all of these derivatives on the x's, is actually related to y by a shift, right? So a derivative is a shift of the entry, right? The derivative here shifts the entry. And so if I want to think about this in terms of indexes, if I want to index everything, the derivative is, there's my derivative, it's a shift by d total entries. And that's because the size of the x vectors, this vector, the size of that vector is d. So it's a shift by d total entries of y, derivative. Since the derivative is a shift by d total entries of y, how many possible shifts can I recover? Well, it's the length of y, and the length of y is n, and I have d total shifts. So I actually have a relationship between all of these, except for the first one up here and the last one down here. So it's actually not nd, it's n minus 1d. So this gives me my n minus 1d extra equations that I need, and this, in fact, is going to be my system of nd equations with nd unknowns. And in particular, it's first order, right? Because there's a first derivative, there's a first derivative, there's a first derivative. We don't have any more, any higher powers of derivatives. We only have first derivatives. So in some sense, you can think about this as the transformation of my original ODE if you want to, or we could just make a definition for capital G. That's what I do right here. We make a definition for capital G, which is exactly the equation that you just saw at the bottom of the previous page. You make that definition for capital G, and then you can recover the actual initial value problem in capital G. Okay, so that's the initial value problem for the derivatives, right? This is the ODE part of the initial value problem. But we also have to consider the initial value part. That's here. And where does the initial value part come from? It's not that hard. It actually comes directly from the definition of y, right? Because if the vector y was just defined as the vector of all of these x's evaluated at any point in time, and certainly the value y evaluated at initial time is just all of those x's, and in fact we were given all of those x's in the original ODE in d dimensions. And so because we already had those from the original IVP, we just directly include them in our new IVP. So this is the new IVP that we're going to solve instead. First order IVP in nd dimensions. And if we solve that, then we can recover the original solution to the original IVP x just by looking at the first d entries in y, right? So keep in mind, this is the first d entries, even though y is nd entries long. We really only care about the first d entries. We unfortunately have to solve all of them if we're trying to solve this equation, but we only care about the first d of them. Let's actually look at an example of this, because this proof is very abstract, and I think you can start to figure out what I mean by the arcane knowledge, because it is really written down in an abstract manner where you have to know what everything is doing to be able to interpret it correctly. Let's reduce the order of a harmonic oscillator. So this is just a second order ODE in how many dimensions? Well, there's only one dimension here. So it's a second order ODE in one dimension. We're going to try to translate this over to a first order ODE in how many dimensions? Well, we have 1 times 2 dimensions. So we're going to do our best to translate this to a first order ODE in 2 dimensions. How do we do that? Well, we follow exactly the procedure of the proof, which says we're going to define the vector y, the 2-dimensional vector, because we're second order, we need 2 dimensions in our vector. We define it as x and x prime. The last term is going to be one derivative smaller than our total order. So the entries y1 and y2 are going to be x and x prime. This immediately gives us that y prime is going to be x prime and x double prime. And there you can start to see this importance in the fact that y2, which was x prime, is the same as y1 prime, right? y2 is the same as y1 prime. This is always how this reduction of order works. y2 is always going to be y1 prime, or as many steps as you need to translate one to the other. And so this is going to be one of our differential equations that we're going to try to solve. Just the fact that y2 equals y1 prime is going to be one of the differential equations. We then have to analyze this differential equation, which we see right there, which we see right there, because y2 prime is x double prime, that means that this x double prime can become y2 prime. So let's actually write that in. This is actually y2 prime. X prime is given right there. It's y2. So let's write it in as y2. And finally, x is right here. X is y1, so we write it in as y1. All of a sudden, you see my original ODE has now become a first order ODE, just involving both y2 and y1. So if we solve this for y2 prime, we recover y2 prime. I'm going to divide everything by 2 and pull the other two terms to the right. I get negative 1/2 y1 minus 1/8 y2. And so in fact, this is now the ODE that we're going to consider between that solves for y2 prime. And we also have this earlier one I mentioned that y1 prime was y2 that we recover just looking at those two. So in fact, it's this combination of these two ODEs that perfectly represents our system. So if I scroll down a little bit, that's what we see right here. y1 prime is y2 and y2 prime is negative 1/2 y1 minus 1/8 y2. We can in fact represent this. Let's represent it with a matrix and vector y. Okay, so if we represent it with a matrix and vector y, we get the following. One derivative on y is the matrix. Let's see where this comes from. What are the coefficients here? The coefficients are 0, y1 plus 1, y2 minus 1/2 y1 minus 1/8 y2. Coefficients of 0, 1, negative 1/2, negative 1/8. That's where the matrix comes from. 0, 1, negative 1/2, negative 1/8. So you can extract the matrix by looking at the coefficients. And now we have a matrix vector ODE. And these are actually really easy to solve. We're going to see why they're easy to solve in the next section. But we got this matrix vector ODE that's in first order, and we can immediately recover the initial values from the original ODE as well. We're just going to jump all the way up to the original ODE, and I'll show you where those come from. Here's the IVP. We have that the initial position is 1, the initial velocity is 0, and so there's my initial position, there's my initial velocity, so we'll get a 1 and a 0 for our initial condition. If I scroll all the way down, there's my 1 and my 0 for my initial condition. So this is how you actually implement this reduction of order for the harmonic oscillator. Let's move ahead and perform reduction of order on a system of nonlinear ODEs. These are going to be much more uncommon for us to see this semester. The earlier case is definitely not unheard of for us to make our lives easier in some situations. This case is maybe a little bit more uncommon, but let's go through it nonetheless. What we're going to do is we're going to start with the following system, and I'm going to omit initial or boundary conditions here because that part is not usually the tricky part of this conversion of a higher order to first order ODE. We consider a system of nonlinear ODEs here. They're actually going to be second order, right? So we have to think about what's the order, second order. What's the number of dimensions? Well, there's x1 here and there's x2 here. And so we have 2 dimensions. And so if we're going to convert this to a first order ODE, how many dimensions do we need? Well, we need 2 times 2. We need 4 dimensions. And that's useful. We immediately know how many dimensions we're going to have to set up, which immediately tells us how to construct y. So you'll notice that I have y1, y2, y3, and y4 because I just determined I need 4 total dimensions to make this work. I'll notice that I always need to set y to be the first 2 entries, and y have to be the actual dependent variables I'm trying to solve for. That's going to be x1 and x2 in this case. And then future entries are just going to be derivatives of the earlier ones. So I'm just going to take derivatives of earlier entries to give me my later entries. And then I can immediately pass derivatives through y to get to y prime is now x1, x2 prime, x1 double prime, x2 double prime. So I'm comparing this to this, and I immediately see that y3, y4 is y1 prime, y2 prime. So here's 2 ODEs that I immediately recover from what I've highlighted in y. I'll say that in y that I immediately recover. y1 prime is y3, and that's just because these are the same, and I recover y2 prime as y4, and that's just recovered because these are the same. So that's nice. I've already found 2 ODEs in y. I need to find 2 more because this is going to be a system of 4 ODEs because there are 4 entries here. Where are the other 2 coming from? They have to come from here. Okay, so how do they come from here? We'll have to find x1 double prime. Here it is. I look at what it is in terms of y. That's y3. So So this is now y3 prime. I'm looking for x2 double prime. There it is. That's y4 prime. I put y4 prime in. x1 comes from here. That's y1. x2 prime comes from here. That's y4. x1 is still y1, so this is y1 squared. x2 is y2. x1 prime is here. It's y3. x2 is still y2, so this is y2 squared. So there's my equations in terms of y3 prime and y4 prime. I have the following. If I isolate them, I'll bring everything else to the right hand side. So y3 prime is negative y1 y4 plus y1 squared, and I have y4 prime is negative y2 y3 plus y2 squared. So I just recovered my two other equations. Remember from earlier, I had written down my first two equations coming from this set. I also have y1 prime is y3. I have y2 prime as y4. So in reality, it's this collection of 4 first-order ODEs that I'm going to be interested in. If I scroll down, I'll see that's exactly what I have here. Here's my 4 ODEs that I just wrote down. So this is how we've reduced now to first order, but we had to increase dimension. So that's a very useful technique in a lot of these solving differential equations problems. However, it's a tricky technique to get used to, and you're always forced to increase the dimension. Some people don't like increasing the dimension that much. It's never really been a problem for me, but if you don't like higher dimensional thinking, it can definitely be tricky. But let's move onwards. We'll move onwards to solving systems of linear constant coefficients, ODEs. This is the sort of thing you may have recovered towards the end of your ODEs experience. This is where you were talking about eigenvalues and eigenvectors probably of some of these linear higher dimensional systems. And we're going to take a slightly different approach maybe than what you took, because this is something that's only sometimes talked about in an ODEs course. It's called the matrix exponential, and it does all of the work of the eigenvectors and eigenvalues for you, but the price you have to pay is an infinite series, okay? So we define a matrix exponential. This is the definition. It's defined e to the tm, where m is a matrix. It's defined as n powers of that matrix, so you're just going to do matrix multiplication on itself n times, and you'll multiply that by t to the nth power divided by n factorial. So this looks exactly like the Taylor series of the exponential. Maybe I'll mention this here. Taylor series of e to the at is going to be the sum a to the n, t to the n divided by n factorial. You may recall that from calculus 2. So that's the Taylor series for the exponential, but instead of putting an a in there, we're actually putting an entire matrix in there. And so we're going to define the matrix exponential like this, and I'm going to scroll down really quick to see why these are important. I'll show you why these are important. Theorem 1.3.6, it's split between 2 pages, but this is why they're important. If I have a vector matrix ODE, you can forget about F for now, but if I have a vector equals a matrix times that vector as an ODE, actually I can solve the ODE with the matrix exponential. So that's what's going on here. E to the t minus t0, m is the matrix exponential. This is this sum, m to the n, t minus t0 to the n divided by n factorial. That's what that term is. And so you can solve these higher dimensional constant coefficient ODEs with the matrix exponential. This is the fundamental theorem. It's one of the most important theorems we have. And the matrix exponential does the job of eigenvectors and eigenvalues for you, as long as you actually are willing to compute an infinite series. Okay, now a computer can never compute an infinite series, but it can get really darn close. So this gives you a way of approximating. If you do this to 100 terms or something, you can approximate the solution very easily. But suppose you want the exact solution. This is where you do need to rely on eigenvectors and eigenvalues. Okay, so that's what this proposition kind of covers for you, is the closed form calculation of the matrix exponential. And the way that this works is that we can define the matrix exponential by an exponential function on the diagonal matrix. Right, so this is the exponential function on the diagonal matrix. But the diagonal matrix is not the same as M, right? If M was like 1, 2, 3, 4, that's very much not a diagonal matrix. M instead, if you've taken a linear algebra course, you know that this is possible, can be transformed to a diagonal matrix. So we call X and X inverse the transformation matrices. And what's in the middle is the diagonal matrix. Okay, so you can transform a lot of matrices to a diagonal matrix, and then you can compute the matrix exponential on the diagonal matrix, and we keep our transforming friends, robots in disguise, on either side of the diagonal, and then they give ourselves the actual matrix exponential back at the end. Now, if you've never gone through matrix diagonalization, you can certainly check out chapter 2 in my other book, as well as the associated videos to that, if you want to see how to diagonalize matrices. If you really don't want to learn how to diagonalize matrices and you've never seen it before, then what I would say is forget about this for now and wait until the next section. We'll see maybe how to approach these when you don't want to diagonalize. And this is probably the approach you saw in your ODEs course if you didn't go through the matrix exponential. But anyway, you can compute these in closed form. Why are they in closed form? Because these are all actual true exponentials of numbers, and then that and that are just matrix multiplications. And so you do get the closed form solution, and they do end up being equivalent to one another. So let's actually cover this fundamental theorem of linear constant coefficients ODEs. Basically, it's what I said earlier. The solution to that matrix and vector valued ODE, so the vector valued ODE where you have a matrix on the right hand side, is going to be given by this, where y0 is my initial condition. But you can imagine it's not uncommon for us to add some forcing functions onto ODEs. So you imagine you have a forcing function, you have to play a game here with the forcing function to recover the true solution if you've added a forcing function. So there's an integral along with another matrix exponential acting on the forcing function. You would just have to compute the entire term if you had a forcing function. Now we can go through a proof, but it's not particularly enlightening. You can go through it if you want. What I have an example of here is actually solving that harmonic oscillator that we found earlier, right? We had taken this harmonic oscillator earlier, and we translated it into the following vector valued ODE using the earlier theorem. So we translated the top one into the bottom one. Now we can actually solve this using our previous proposition. This can be solved with the matrix exponential, but we need to find the matrix exponential. So there's our matrix, 0, 1, negative 1/2, negative 1/8. We need to find the matrix exponential. Okay, so the way we're going to find it is by diagonalizing, and it looks pretty bad. If you diagonalize this, you end up with the following. This 16 should be in the denominator here. But you end up with the following diagonal matrix, where we have some complex entries, and you end up with the following two transformation matrices. That's diagonalizing it, which means if we took the exponential, what we have to do is take the exponential on both diagonals, and we end up with this diagonal, where the exponential is on the diagonals. And then we compute out the inverse and the forward transformation, and we end up with the following really ugly looking matrix. But this is, in fact, the matrix exponential of 0, 1, negative 1/2, negative 1/8. Looks bad. There's not too much you can do in the real world when things look bad. I mean, bad problems exist. So you end up with that matrix exponential. If we scroll up just a little bit, the previous theorem, the fundamental theorem of ODEs, says that the solution, when I have an initial condition, so here's my initial condition, 1, 0, is the matrix exponential acted on the vector, which is the initial condition. Okay, so I'm going to act this matrix exponential on the vector 1, 0. That's matrix times a vector. And if I compute the matrix times a vector, what do I get? I get the following vector. Now, this looks like a matrix because it's so wide, but it's actually a vector. So you'll notice all the terms are added together. So I get that vector. And then if we jump back to trying to solve the original harmonic oscillator, every time I solve the reduced order problem, the true solution is only the first entry in the reduced order problem, or the first d entries, where d was the dimension of my original equation. So this is the dimension of my original equation, it's just 1, so I'm only looking at the first entry, and that's where I'm recovering this as the solution to the original harmonic oscillator ODE. Now that's going to seem way more complicated than anything you ever covered in ODEs if you didn't take my course or somebody else's more advanced course. And so you're going to be wondering why it's even useful to try to solve ODEs like this. And I'll be honest, it's not useful to solve harmonic oscillator ODEs like this. The problem is when somebody gives you an ODE that looks like this, when someone gives you an ODE that looks like that, you're going to have no choice but to solve it in the way that we were just solving ODEs. So harmonic oscillators are a very special case of ODEs that your life gets easy. But somebody can certainly give you a very, very tricky ODE, and you may be expected to solve it, and if you haven't practiced anything more complicated than a harmonic oscillator, you're going to be stuck, right? And so I'm giving you the example of the harmonic oscillator. You're going to wish that you had solved it a different way. You're going to wonder why I'm wasting your time. But it's not the fact that it's a harmonic oscillator, it's the fact that this is a simpler problem to try to solve. And it's going to give us practice for when we encounter much trickier problems. And I have this remark about how ugly our solution is and that the real world is an ugly place. You know, you're not necessarily going to get nice answers when you're out working on a job. You can't expect 1s, 2s, 3s, and 4s to be the only numbers in your solution. And so I'm going to try to balance practicing with ugly numbers in this course with an ease of computation. Okay, so sometimes we're going to get easy numbers in our computations, other times we won't, and we're going to try to practice with both. Okay, so the earlier subsection I had called linear constant coefficient ODEs. Now, either one of these two, linear or constant coefficient, could be violated. I could have a non-constant coefficient ODE, or I could have a non-linear ODE, and they're both going to give me different solution methods that I'm going to have to rely on. This fundamental theorem that I gave you really only applies to linear constant coefficient ODEs. And so we're going to try to understand the other two cases of ODEs within the next two subsections. So let's look at the case when I violate constant coefficients and I now have non-constant coefficients. That would mean that maybe this matrix M depends on time. It evolves over time. Some of you may have learned this as a non-autonomous ODE or a non-autonomous Cauchy problem. They're all kind of the same thing, but it's still linear because the matrix M, right? Matrices are linear maps. So we're allowing ourselves only linear maps. We're going to stay in the realm of linearity, but we're giving ourselves the ability to change over time. Maybe the matrix changes over time. Now the solutions here are so much worse. There's a reason why we call the earlier one the fundamental theorem, because we actually have a really useful theorem in the case of constant coefficients. The moment we have non-constant coefficients, everything goes out the door, and I've introduced the following proposition. I'm barely going to cover it right now because it's not the sort of thing that I can expect any of you to use. I barely can use this half the time because it's so hard to use. If you've taken my previous course, I covered the Magnus expansion. That was a situation that we were trying to solve one of these in as well. And there's just not really a good way to solve these the way there was with constant coefficient ODEs. So I will introduce this theorem right now, but then we'll move on to a corollary, which is a specific case, and the sort of specific case that's going to be useful for us. So let's take the following non-constant coefficient ODE, linear. We can find a solution, and the solution looks fairly similar to our solution to the previous ODE. This should be a T0 when we had constant coefficients, but you'll notice what I've done is I've replaced the matrix exponentials with capital Y. Okay, so instead of having matrix exponentials, I've got these capital Y's. You may be wondering, what are capital Y's? Well, capital Y's are what are called fundamental matrices. Okay, so these are fundamental matrices. Of the ODE. And we need to find them somehow. So in the case of linear constant coefficients ODEs, the fundamental matrix was the same as the matrix exponential. That's why my life got easy. In this situation, it's not quite as easy as being the matrix exponential. I instead have the following. There is a matrix exponential here, but we have to be careful about what this means. This is a matrix exponential. At the point S. And S is in this range of T0 to T. So you evaluate it at a point and you can compute the matrix exponential. But then what do you have to do? You have to take this very interesting notation that I use here, that I call the flow product. And this notation, I have a ds here in the power. You'll notice that this notation, what I'm trying to do is I'm trying to say that you're actually taking the infinitesimal power, of the matrix exponential, and you are composing infinitely many of them. So you compose infinitely many of them over this range of T0 to T, and you're going to compute the matrix exponential and then take its infinitesimal power. And that's going to give you the fundamental matrix. to actually try to do this in any meaningful sense is moot. It's just impossible. This can't actually be done in 99.9% of situations. And so this proposition, although you can state it, is not the most useful proposition. I'm going to skip through the proof. I'm even going to skip through this thing that I was calling the flow product. By the way, that's the Icelandic letter thorn, if any of you are curious. It's thorn from the Icelandic alphabet. So that's kind of fun. I decided to come up with that notation. Anyway, we're not going to worry about it. I've got the remark. I define it for you. We're not going to worry about it because you can't do anything with it. I can sometimes do some things with it as a PhD of math. It's a really tricky thing to use, so we're not going to worry about it. Instead, we have the following corollary. This is what you should study. I'll say this is the useful. This is the useful result. It's this corollary. It's that we can actually find a solution using the matrix exponential of an integral. Okay, so it's my fundamental matrix has reduced to a matrix exponential of an integral. So it's e to the integral of a matrix, and that's going to be my fundamental matrix. And that's not very hard to compute because you can integrate a matrix entry-wise. So you just look at each entry. I don't know how to spell that. You integrate a matrix entry-wise. So you look at each entry in the matrix and you just integrate that over time. That's how these integrals work. But the solution only works under the following. This is the primary requirement, the number one check you can give to try to solve a non-constant coefficient linear ODE or system of ODEs. So this is the fact that the matrix at one time, and then you take the matrix multiplication with the matrix at a different time. So you're comparing two different times of this matrix because it evolves over time. That needs to be equal to the matrix at the different time times the matrix at the earlier time. And to make this make any sense, you should recall matrix multiplication is not commutative, i.e. you can't switch orders. You can't usually switch orders. Okay, and it's this fact that you can't usually switch the order of a matrix multiplication that makes this a very restrictive property. Okay, so the fact that you can switch the order here, the equal sign is saying we can switch the order. The fact that we can switch the order here is a very restrictive property. Okay, so just keep this in mind. First thing to check when solving is that this is a true property. If this fails, then you can't apply the corollary, and then you're basically stuck, which is unfortunate, but also why ODEs can be interesting. If this always applied, ODEs wouldn't be interesting. We would know how to solve all of them. Okay, so let's see this in action. I'm not going to go through the proof, but let's see it in action on the following IVP. So the following IVP, it's first order, it's in 2 dimensions, and here's the interaction between the two of my dimensions. I've got coefficients of 1 over t, 3 over t, 2 over t, and 2 over t. You should immediately be able to recover that with these 4 coefficients, the matrix I'm looking at is really 1 over t, 3 over t, 2 over t, and 2 over t. Those are my 4 coefficients. And then, what is the first thing I need to check? First check if m t1, m t2 equals m t2, m t1 for any choice of t1, t2. So that's my first check on all of these non-constant coefficient problems, that the following is true, and I go through that check right here. You just have to write it out. It's not the hardest thing in the world to do, but you write it out. There's mt1, there's mt2. I compute them together, and I get the other matrix squared times 1 over t1, t2. I can then split in the opposite direction because this multiplication is commutative. There's no matrix, thankfully, on that multiplication. So I can change the order there, resplit it up, and I end up with the opposite direction of matrices. So there's a big check mark in making sure that my matrices actually commute, which means that I can compute the solution from the solution formula up here. There it is, right? I can compute the solution. I could do the whole thing, but because there's no forcing term on my problem, I'm really looking right here for my solution. I'm taking the exponential of the integral of the matrix and acting it on the initial condition. So So if I scroll down, I'm taking the exponential of the integral of the matrix, and I'm acting it on the initial condition. I go ahead and integrate. So from 1 to t, it's not too bad to integrate, right? Integral 1 to t, 1 over s ds. What do I get? I get the log of, I'll do that log. I get the log of s from 1 to t, which is the log of t minus the log of 1, which is the log of t. So if I had something like e to the log t times this matrix, this is really t to a power of a matrix, which we can compute it this way. Lots of choices on how to compute that. The result is the following. And so that's this term. And then this matrix just needs to hit the vector 5, negative 5. And once I let the matrix hit the vector and simplify things, I get my solution, which is 6t inverse plus t to the 4, or minus t to the 4th, minus 4t inverse. These are supposed to be minuses, by the way. Typos abound. First time you write anything, there are minuses. Negative 4t inverse minus t to the 4th. And so you're able to find the solution. You can certainly go in and check that that is a solution to this IVP. We've got one more example. This example is an ODE in just one dimension. And I introduced this example because the previous corollary always applies in one dimension. That's why I've introduced this here. One dimension is our special dimension where everything is easily solvable and I can always apply that previous corollary. And so in this case, I just have to pay attention. What is my matrix? It's hard to see. That's my dependent variable. So the multiplier, t squared, is my matrix. So in fact, this is my matrix M of t. And I do have a forcing function here. It's whatever's left over. There's my forcing function, negative t squared, e to the negative t cube over 3. And I apply the previous corollary that I said always applies in one dimension. Here it is. I'm going to take e to the integral of the matrix, multiply by the initial condition, add the integral of e to, now the integral goes from s to t of the matrix, act it against the forcing function. And what does that look like here? Here's my e to the integral of the matrix. There's the initial condition. Here's the integral from the initial condition to time of e from s to time of, there's the matrix, against the forcing function right there, ds. And you compute everything out. What you get is 1/2 e to the negative t cube over 3. You can verify that that solves the ODE as well as the initial condition. Okay, so we're getting long on time, so I better stop there. We'll get into the system of nonlinear ODEs in the next section, as well as I'll go through quite a few of section 1.4, just using the table of solutions to help us get answers in some easier problems. Anyway, that's all I've got. Thanks for sticking with me. See you next class.